The second problem is the area. And that is found area under y equals f of x from a. So what is this? What is this area with the curvy? These are the two classical problems, calculus, and I don't know about you all, but they don't seem like they got anything to do with it, right? One of them is like finding the slope of the tangent line. The other one is like finding this area in the curve, right? It seems like two completely different questions. However, it is going to turn out, we're going to see kind of at the near the climax of this course, that these two problems are actually very intimately related. But for now, you all probably haven't looked at this one yet, and that's fine, because this will be sort of later in our course here. But you all have looked at this problem here. And it's strange because, of course, one might look at this and say who cares, but it turns out that everything in science, economics, medicine, all kinds of things like this, what's important is not just knowing something, but knowing how it's changed. Right? I mean, if you've got a certain amount of money in the bank, that's all very well and good, but I'd much rather see the change in the amount that I have in the bank be positive rather than negative. Right? Rates of change are very important. Right? And so, in the first problem, the tangent line problem, it turns out that this is kind of, it looks kind of abstract math or something like that, but it actually is doing something far more sweeping and deep. It's about rates of change. Let's ask about this problem. Suppose I have some function here. And let's suppose, just for giggles, that I take a particular point on this. Okay. And suppose that I want to find, I'm going to draw this as best I can, the tangent. Right. Suppose I want to find this. Now, let's go back old school. I want to find that red tangent line, correct? What information do I need, say back from algebra 1, to find a line, to determine a line? How much data do I need? What's it?
Just determine a line.
To determine a line. Well, if you have a single point, the problem is, might be all kinds of lines. So you need a little bit more. 2 points will do it, right? Once I nail down these 2 points, as long as they're 2 different points, then I'm good to go. Okay. How about a single point and what other piece of data? Okay, the slope. So a line is determined by 2 points, as you say, or it can be determined by a point and a slope. That sort of narrows down this first problem, right? You can have all kinds of lines that go from this point, but once you tell what the slope is, it sticks it, right? Actually, there's only one exception in the case. 2 points technically your intersection, right? Because there's one case where the point and the slope is a little bit off. Anybody tell me what that is? What's wrong with that? What's the slope of it? It's undefined. And that's the problem, because I really can't say what the slope is here. But if you have 2 points that determine a vertical line, it's better. But here we'll assume that the line is not vertical. Right. Now here was the whole calculus idea. The whole calculus idea. Really, what we need here is if slope of red line is M, then I can tell you exactly what the tangent line is. And all I have to do is use like the point slope. It's y minus f of a is equal to m times x minus a. Y'all remember this point slope form of a line? Y minus the y coordinate of the point. And remember, f of a, that's just, y minus f of a is slope times x minus the x coordinate. It's the old point slope. What do I know? I know what a is, it's a. I know what f of a is, it's whatever I can get plug in, but I don't know what n is. What was the tool that you all developed in 1040 to find out what that m is? M is the missing piece of the puzzle. The derivative, right? That was the whole idea. And do you remember how you sort of went about that, or maybe what the genesis of the derivative is?
X plus h minus x.
Right. That's right. That's basically the gist of it. The idea is there's nothing that you've learned in algebra trigonometry up to this point that's going to tell you what slope is. And so you do what a lot of good engineers would do, and that is you approximate. That's the practical drawing, but you take this point here, a plus h, and f of a plus h. Notice in this case, my h is actually negative, right? Because I go from the way I've drawn it, h is negative, but that's okay. It doesn't matter. And what do? Is you measure the slope of this very poorly drawn blue line. The slope of the secant line. Y'all heard that terminology called secant line. Right? Well, that's just f of a plus h minus f of a. That gives me my rise, which I guess in this case is negative. And what's my run? So f of a plus h minus f of a, that measures my change in my y coordinate. How much my y coordinate? How much my x coordinate change? A plus h, take away a, which is h, right? Now, does it look like the slope of the blue line is exactly the slope of the red line? I agree, it doesn't look like it. How can I make it better though? Right? This is kind of a crappy, it looks to me like the blue line has sloped a little bit less than the red, right? What if I wanted a better approximation? How could I adjust this to make a better approximation? Well, so I'm keying on this. All I want to do is make this point closer to this. So well, yes, you're ahead, you're a bit ahead of my piece of the brain. So, but yes, that's exactly where we're going. So you take one that's a little closer. And does it make sense to you all that as you get closer and closer, this point and the red point, this point, the red point, so you get closer and closer, it looks like the slope is getting closer to what the red line slope is, right? And so this is the genesis of what you were talking about, this whole idea behind the limit. So the tangent line is this difference. And then take the limit as h goes to 0. That was the whole idea behind this right here. And this is where the notion comes from, the notion of derivative. It is basically, and of course you need to know when this exists. Right. So for example, well, it's 2 y x squared. So x add, give me a number. Well, we need to find let's look at the limit as h goes to 0 of f of right, because what I want to do is I want to find the sort of tangent that x is 2. So it should be f of 2 plus h minus f of 2. Everybody cool? Now let's just plug this in and see what shakes out. F of 2. Well, just plug this in here and I get 4 plus 2 is 6. It's also the y coordinate here, so I have that. Here's the trickier part. What is f of 2 plus h? Now, unfortunately, it's a little bit more complicated. This is f of x. Now I've got to replace every x with 2 plus h. So it's actually 2 plus h squared plus 2 plus h. Right. And now we've got this mess to look. But see, here's kind of a good thing. If I multiply this out, this becomes 4 plus 4h plus h squared plus 2 plus h minus 6 h. Now notice this is a mess. I'm cleaning it up. Four and 2 minus 6 is 0. That's convenient. And actually, that's kind of a hint to me that I've done something right. What am I left with? H squared plus 4 and 1 is 5h over h. Now, one of the things I remember about limits is the first thing I always try to do is be a bonehead and plug it in. But in this case, it's 0 over 0. Whenever you get 0 over 0 or infinity over infinity, that's like a message from God telling you that there's more work to be done. And there's more work to do here. I mean, like, what it is. Back on next. A limit means you're close to 0, but you're not exactly 0, which means you cancel. So let me answer the question. Slope is 5. If you want to multiply that out, it's y equals 5x minus 4, but I don't care. So let's go a little bit farther. Let's use the definition of derivative to find the derivative of this thing. It's not that much more work. You all know, I want, so let's just do this easy, but you all know. 2x. Okay, let's, good, 2x plus 1. Does everybody remember the formula times x, first power, third x? And notice what happens to this when you plug in x equals 2. What do you get when you plug in? You might have had a problem like this. Use this definition of derivative. Find derivative of um, well, probably from 240 does slip formulas is quicker, but it's important to remember this definition of derivative because in particular, when this limit can't be worked out well, it allows you to get approximation. One reason, many. I know what h is, it's h. I know what f of x is. It's x cubed plus 3x squared. F of x plus h should be x plus h cubed plus 3x plus h squared. This is the limit. It's x equals to 0. I have to go through the find this out. Such x cubed is 3x squared h is 3x squared plus h cubed. Then multiply this out. 3x squared plus 6xh plus 3h squared minus x cubed minus 3x. Now, something wonderful happens to me. Because all the stuff that has no H's in it goes away. Notice, there's an X cubed here, and it's killed by that. And there's a 3x squared here, and it's killed by that. And everything left over has an H. This is actually kind of, I follow from the right side. This is 3x squared H plus 3x squared plus H cubed plus 6x H plus 3h squared over H. Now, since H is not exactly 0, I can cancel one factor of H everywhere. So everybody okay with that stuff? Now, notice the it's H. And it's H goes to 0, that's going to go away. That's going to go away. That's going to go away, leaving the only 3x squared plus 6x. How many of y'all knew what the answer was supposed to be? Okay. Any questions? Let me review. So once you have derivatives, I'm going to see what you guys remember. So let's kind of go. What's the derivative of x? Where n is the number of this. That ring a bell, right? How about this? Oh, my favorite, right? Do you know the more general? Did they teach this in particular? Well, no, because it should match this if A and E are the same. It turns out, right, I'm right, I'm sure. This is A to the X. That's the natural log. In a couple of sections, I'm going to show you why this is true. I wouldn't be surprised if you've seen this, and I wouldn't be surprised if you have not seen it. But here's kind of a good gut check. This is how math always takes care of it. Notice when A is E, you should get this formula, right? What happens when you put A and E in here? You get derivative of this is e to the x times the natural log of E. And what's the natural log of E? So, okay, how about this? Derivative of sine? Good. Derivative of cosine? Good. You know, derivative of tangent? What happens if you forget? You know? Guy like me, parents who are cousins and all, maybe I forget. How can I get this back?
I just wrote it out. It's fine.
Well, I can't learn from that. But there's nothing, so I'm gonna do this. Here in my formulas, I'm gonna assume that F and G are differentiable. So you can take your. How about this? Well, so here's, yeah, it's easy to get this. Bottom square, you get a new fraction, square the old bottom. Then it's bottom times the derivative of top. Minus top times the derivative. Now, probably one of the last things that you learned is important is chain. Like, you can sneak the thing I'm doing. This is the same thing as this, isn't it? Okay. Let's dissect this. What does the product rule tell me? The product rule tells me, hey, derivative of this times this other garbage plus this. All right, now I'm going to derivative of this. How do I do the derivative of g of x to the minus 1? Okay, good. It's not quite finished. What are you gonna multiply it by? Good. Derivative of what's inside the block. And so what this is f prime of x over g of x minus f of x g prime of x over g of x squared. Right here. Let's just rewrite this as a fraction. And now I can put an extra g of x here. I'll do this dramatically. G of x, g of x. So that now I have a single. This is g of x squared. G of x f prime of x minus f of x. And here I can get the closure. So once you know the chain rule, you can forget the closure rule, but I wouldn't, because in many cases, sometimes the closure rule can still be implemented more quickly. But it is the chain rule that gives people sometimes a bit of a heartache. So I want to go through the chain. Is everybody familiar with all this? Remember the product and the closure rule? Well, what about the chain rule? Let's let. What bias? Let's get to the river of this. Okay, I think it's a good idea. I always put in more parentheses that will help you along with it. Now, doing the chain rule is basically being good. The first thing I come to is sine of whatever, sine of block. What's the derivative of sine of block? Cosine. So there we go. And I work my way inside the parentheses. I gotta multiply by the derivative of what I find inside. And the derivative of what I find, or what I find inside there is e to the block. What's the derivative of e to the block? That's right, everybody's, e. But I'm not done, because I gotta multiply this by the derivative of what I find inside there. What's the derivative of x squared? And there you go. That's, what's the first thing that comes to? That's right, it's some crap to the 1/3 power, block to the 1/3. And what is the derivative of block to the 1/3? Am I okay with that? We totally calm. Now I've worked my way inside. First parentheses. Now I've got to multiply by the derivative of what I find inside here. Now, what's the derivative of what I find inside here? Well, this is easy, right? Derivative of x squared is what? 2x. The other piece is a little bit more complicated. Right? It's sine of block. What's the derivative of sine of block? It is cosine. Okay. See, I'm done taking the derivative of this, but I'm not done taking the derivative of this. Now I've got to multiply by the derivative of what I find inside here, which is this thing. So I'll multiply this. What's the derivative of what I find inside here? Derivative of x cubed. And what's the derivative of x e to the x? What do I got to do there? So derivative of x times e to the x plus x. And they're even. Any questions on it? Okay. So let's do one more. Yeah, so quick here. Might get out a little early today. Okay. What if I did this? That one's kind any suggestions on what the first step should be?
Side. It's fine.
Well, right, I mean, I agree, we're gonna have to do like the D outside and all this, but I really think,
It'll,
how do you suggest?
set like, for his first, I read this for, but like, say like all these different, so like, go like that. And then
Right.
just keep going to like one third, fourth.
Agreed, right, I think I think that's a very sagacious move, but I think what you want to do is write this. So let's think about, let's work our way inside out. You have x plus one with a 1/5 power. Right? So if you were to compute this number, you would take whatever x is, add one to it, take the 5th root of it, then you would add x back to it. And take the 1/4 power of that. And then add x to it. Take the 1/3 power of that. And then add x to it. Take the 1/2. Uh, let's try this. This is not terribly hard, but it is very easy to lose your place, so just be careful. First thing I come to, let me count my parentheses, make sure I did this right. 4, 1, 2, 4, 5. I get 1/2 block. Third minus 1/2. Now I have to multiply by the derivative. I'm gonna run out of color tone in this. So I have to multiply the derivative of what's inside here. Which is the humble x plus a mess. The derivative of x is 1. Derivative of this, well, it's blocked at 1/3, right? So it should be 1/3 of x plus 5th 1/4 minus 2/3. Now, I'm not done. I'm done taking the derivative of 1. I'm not done taking the derivative of this. So I've got to multiply this by derivative of what I find in here, which is x plus block of 1/4. So this is 1 plus, I have block of 1/4. 1/4 x plus 1, 1/5, the minus 3/4. And I'm not doing taking through this. I've got to multiply this by the derivative of what I find inside. And this was a little bit easier, finally, because this is 1, derivative of x is 1, plus 1/5 x plus 1, the minus 4/5. Close that off. Close off blue. Close off green. Yes, it's very easy to kind of get lost in all the. Notice, none of the derivatives, none of the separate derivatives that we took were very hard, were they? Because every one of our derivatives was log to the 1/4, 1/3. It's easy to take derivative. The hard part is making sure that you're careful about keeping up where you're supposed to be. Okay, any questions? Okay, I'm gonna give you all a first quiz today. Hopefully there'll be time for you to finish up. I know that you're gonna be pushing it. In general, I'll start giving quizzes about this time, but we'll have till later. Um, so you can turn this in when you're done. Please look over, especially some of the chain rule problems. We will officially start new material tomorrow. And there's your quiz. I designed it to kind of be challenging. Just do your best and remember the quizzes are all covered. So
You know,
I would appreciate if you do it on different quizzes.
What's that?
Yeah, it's great. I would prefer. I could let you have. Yeah, I can. Drop that. You do it on your iPad, how you can submit. Keep that, that'll be fine for today, just try to remember it today.